Today we are going to derive the electric field of an infinite line of charge using Gauss's law. We start with the fundamental equation, Gauss's law. It states that the total electric flux through a closed surface is equal to the enclosed charge divided by epsilon naught. Now imagine a cylindrical Gaussian surface around our line charge. The total flux is the sum of flux through the three specific parts: the top cap, the bottom cap, and the curved side. Now let's look at the flat ends. The electric field points radially outwards, but the area vector points up or down. Since they are perpendicular, their dot product is 0. So the top and bottom caps contribute nothing to the flux. However, on the curved surface, the electric field and the area vector points in the exact same direction. They are parallel. This simplifies our integral to just electric field magnitude times the area. Putting it all together, 0 plus 0 plus E times area must equal the enclosed charge over epsilon naught. We know that the curved surface area of a cylinder is 2 pi RL. The charge enclosed inside the cylinder is the linear charge density lambda times the length L. Let's substitute these values back into our equation. Notice that the length L appears on both sides, so it cancels out. We are left with our final result, that is, the electric field is lambda divided by 2 epsilon naught r. It decreases as we move further away, that is, inversely proportional to distance r. I hope it helped. If it did, make sure you like and subscribe to the channel. I'll see you in the next one. Thank you for watching.